Hello everyone, my name is Suvrat and today I'll be discussing Codeforces Round 1062. Div 4. So let's start with the discussion. Problem A. So you are given 4 sticks of length A, B, C and D. You cannot break or bend them. Determine whether it is possible to form a square using the given sticks. So problem A. So I am given 4 sticks of length A, B, C and D, and I need to check whether I can make a square out of these 4 sticks without breaking or bending them. So basically a square looks like this, where all the 4 sides have equal length, and since I cannot break or bend these sticks, I need to use these sticks individually as one of the sides. So for these 4 sticks to be able to make a square, all of them should be equal. So basically if A is equal to B is equal to C is equal to D, then the answer is yes, else the answer is no. So this is O of 1 time complexity. We can see the test cases. So 1, 2, 3, 4, since they are different, the answer is no. 1, 1, 1, 1, the answer is yes. 2, 2, 2, 2, the answer is yes. 1, 2, 1, 2, the answer is no. 1, 1, 5, 5, the answer is no. 5, 5, 5, 5, the answer is yes. 4, 10, 5, 9, the answer is no. So I'll show you guys the code for this. So basically the test cases, then I need to take input 4 numbers. So here I am basically using a set. So set is basically a data structure which will store all the different integers. So if all the 4 numbers were same, there will be only one element inside the set. So if there is only one element inside the set, the answer is yes, else the answer is no. So this is the code for problem A. Let's move on to problem B. So problem B is, Kirba is writing his girlfriend's name. He has n cubes, each with one lowercase Latin letter written on it. They are arranged in a row forming a string S. His girlfriend's name is also a string T consisting of n lowercase Latin letters. To prove his love, he must check whether it is possible to rearrange the letters of string S so that it becomes her name T. And the constraints are, there are 1000 test cases and n is till 20. So I think we'll be allowed till n square, maybe n cube also. N cube is 8000, so 8 into 10 to the power 6. N cube also will work. So time complexity is really not an issue here. So let's see. Problem B. So we are given two strings, string S and T. And we need to check if T can be, S can be arranged to form T. Check if T can be formed by rearranging S. So Humitsa, let's see the test cases. The first is Humitsa Mitsuha. So we can see that this can be rearranged into this, I think. Yes, so basically M, I, T, S, U, H and then A. So this can be rearranged into this, so yes. And then Orhi, Hori and Hori. So again this can be rearranged since H, O, R and I. So yes. Then Akima, Makima. So M, A, K, I and then we don't have another M. So basically here there are two M's, but here there is only one M, so we cannot rearrange this into this. So the answer will be no. Nezuko. So we clearly have a Q here and we have a K here, so this cannot be rearranged into this. Mikasa, Mikasa. So the answer is yes for this also. So basically what we need to check is simply if the frequency of letters in both S and T are same, then S can be rearranged into T. This is quite obvious because if the frequency of each alphabet is same, then we can just position them to their specific positions in the string T and S will be rearranged into T. But if some alphabet has different frequencies in S and T, then no matter what we do, we cannot transform S into T by rearranging the alphabets. So we need to check if the frequency of alphabets in both S and T are same or not. So there are many ways to do this. What we can do, one thing we can do is we can create two frequency counters for S and for T. So this is frequency counter for S, this is frequency counter for T, and what we can do is for auto I in S. So this I will be a character. So we can do FRS of I minus integer of I minus integer of A plus plus, and similarly for T, same for T, basically this colon T FRT this. So similarly for T, and then we can check for I equal to 0 till I less than equal to 25 I plus plus. We can check whether all FRS of I is equal to FRS of T or not. So this is one way. Another clever way of doing this is we can do sort both S and T. So what does sorting mean in a string? Let's take an example. Let's take the first test case, Mitsa, Mitsuha, HUMITSA, MITSUHA. So basically when we sort this, it will look like A, I, E, F, G, H, okay, H, then I, M, S, T, U. So this would be sorted, and when we sort this, again same will come. So we can just compare if both the sorted versions of S and T are equal, then S can be rearranged into T, otherwise not, because sorting would simply put the earlier alphabets in the beginning. So basically it would be the same as checking whether the frequencies of each alphabet are same or not. But the code here would be a lot more simpler since we have inbuilt function for sorting in C++. So this is another way to solve this. Also we can use map and stuff as well, that is your choice. So I'll show you guys the code now. So basically I take input the two strings and I sort them and I check if both of them are equal or not. If they are equal, then the answer is yes, else the answer is no. And the time complexity of this would be O of n log n, since sorting the string takes O of n log n. So the time complexity is O of n log n. Now let's move on to the next problem. I am audible, right? Yep. So the next problem is Ismatdin has n toys arranged in a row The ith toy has an integer AI. He wanted to sort them because otherwise his mother would scold him. However, Ismaddin never liked rearranging toys in order, so his friend Jahonli X gave him a magic wand to help. Unfortunately, Jahonli X made a small mistake while creating the wand, but Ismaddin couldn't wait any longer and decided to use the broken wand anyway. The wand can only swap two toys if their integers have different parity. One is even and the other is odd. In other words, you can swap toys in position I, j only if AI mod 2 is not equal to AJ mod 2, where mod is the remainder of the integer division. Now he wants to know the lexicographically smallest arrangement he can achieve using this broken wand. And the constraints for this question is n is still 2e5, AI is still 1e9, and there are 1e4 test cases, and the sum of n over all test cases does not exceed 2e5. So since we are given this condition, the expected time complexity of solving each test case would be O of n or O of n log n. Since O of n square would not work, since that would mean 4e10 operations, which is beyond the limit. So problem C. Here basically we are given an array where we can do the following operation. Swap I comma j, swap AI comma aj actually, if AI and aj have different parity. Basically, what is parity? Parity is nothing but even or odd or even. So if AI is odd and AJ is even, we can swap them. If AI is even and AJ is odd, we can swap them. But if both are even or both are odd, we cannot swap them. And we need to find the lexicographically smallest array possible. After the operations. So let's see the test cases. The first test case is 2314. So since we need to make the lexicographically smallest possible array, right? Lexicographically smallest is nothing but alphabetically smallest. Something like that. So since we need to make the lexicographically smallest array possible, we obviously know that 1 is the smallest integer here in this array, right? So the lexicographically smallest array would obviously have 1 in the beginning. So first operation what we can do is we can swap these two. So the array will become, let me write it below it. The array will become 1, 3, 2, 4. Then what we can do is, since this was even and this was odd, this operation was possible. Now what we can do is, since 2 is smaller than 3, right? So we can again swap these two to get the array 1, 2, 3, 4. And this is actually the lexicographically smallest array that could have been possible with these integers. So this will be the answer. So the answer for first test case is 1, 2, 3, 4. And now the next test case is 3, 2, 1, 3, 4. 3, 2, 1, 3, 4. So we see that again, to make it lexicographically smaller, we need to put this 1 somehow in the beginning. But we currently are not able to perform that operation since 3 is an odd number and 1 is also an odd number. So let's try to, in order to put 1 here, we need to put some even integer here first. So what we can do is first we can swap these two. What happens when we swap these two is 2, 3, 1, 3, 4. The array looks like this. And now basically what we can do is we can swap these two. 1, 3, 2, 3, 4. Right. Now again we can just swap these two so that 2 comes before 3. So 1, 2, 3, 3, 4. So this is again the lexicographically smallest possible array. So this will be the answer. Now the next is 3751. Now what we can see here is all the numbers are odd. And since all the numbers are odd, there is no operation that we can perform here in this array. So the answer would remain the same, 3751. Again, here all the numbers are even, so the answer will be remaining same. All the numbers are odd, so the array remains same. So basically, one observation, this is pretty obvious though. If all numbers are odd or all numbers are even, then the answer is the original array. Now we need to solve for the case where not all the numbers are odd or even. So 25317, let's check this out. 25317. So let's again start with the same strategy. We see 1 here, so we'll try to put 1 in the beginning. So we will do this operation, 1, 5, 3, 2, 7. Now again 2 and 5 are different parity, so we can perform this operation. So 1, 2, 3, 5, 7. So the answer for this test case will be 1, 2, 3, 5, 7. And we know, and I'm not trying to further improve this answer because we see that this array is the sorted version of this array. 1, 2, 3, 5, 7 is the sorted version of 2, 5, 3, 1, 7. So obviously sorted is the lexicographically smallest array possible. We cannot make this array further smaller lexicographically, since sorted means all the smaller elements are in the beginning. So basically this is the lexicographically smallest possible array with these elements. So that's why I'm not trying to further improve this. So 1, 2, 3, 5, 7. So the next test case is 2, 4, 8, 6. Again we see that all are even. So the answer will remain same. So I think although many of you must have already noticed, but let's see it separately as well. So we solved this one case where all the numbers are odd or all the numbers are even, right? Now let's see the other case where not all the numbers are odd, but there are some even as well. So let's take some array actually. Let's take 3, 1, 7, 5, 9, 11, and let's take a 2. So let's try and make the lexicographically smallest array from this. So obviously 1 I will need to have in the beginning, and we see that 11 is in the beginning and 11 is also odd, 1 is also odd, so we cannot do the swap right now. So what we can do is, since we have an even number, we can put the even number here, 2, so the array becomes this, and now we can put the odd number here, 1, 3, 2, 7, 5, 9, 11. So now we have 1 in the beginning, and what we can do now is we can perform this operation. Just let me perform this operation and you guys will notice. So after I perform this operation, what will happen is 1, 3, 11, 7, 5, 9, 2. If we look at these 4 operations, these 3 operations as a single operation, Basically in the array we literally swapped 11 and 1. 3 is in its position, 7 is in its position, 5 is in its position, 9 is in its position, and 2 is also in its position. So after these 3 swaps, we essentially swapped 1 and 11 only. So we performed a swap between two odd numbers only. So how did we do that? Let's see that again. We first put an even number in place of 11, so it became 2, 11. And then we took the odd number that we needed originally in that place and put it there. So I put 1 here and 2 comes here. And now since 2 was originally in the end, so 2 will again go back to its place and 11 will come here. So basically what I am trying to say is, if there are two odd numbers and an even number, we can basically swap these two also. We can perform this operation. How? Basically we can swap these two. Let's make them O1 and O2. We swap these two, so it becomes EO2 and then O1. And then we can swap these two, so it becomes O2E and O1. And then we can swap these two, so again it becomes O2, O1 and E. So after these three operations, the array was initially O1, O2 and E, and in the end it became O2, O1 and E. So the observation I am trying to tell here is, if there is at least one even number, then we can swap two odd numbers as well. And similarly, if there is one odd number, we can swap two even number as well. So now in the cases where there are both the odd numbers and even numbers present in the array, we can essentially now perform any type of swap. We can swap the odd numbers with an odd number, and we can swap an even number with an even number, and odd and even we can swap already. So basically we can swap any two numbers, and if we can swap any two numbers, we can rearrange the array in any way we want. So basically, since we can rearrange the array in any way we want, the answer for cases where there are both odd and even numbers will be sorted array. So basically we will just sort, because sorted array is the lexicographically lowest array possible. So we can just sort, and that would be the answer. So I'll show you guys the code for this now. So first I'm counting the number of odd and evens. So I'll input the vector, and then I'll count the even and count the odd. So if even is n or odd is n, that means the whole array was of the same parity. Then I will just output the array as it is, since I cannot do any operations. Else I will sort the array, and then I will output the sorted array, since that is the lexicographically lowest possible array. So that was the code for problem C. The time complexity of this code will be O of n log n, since we are sorting. And that will be well within the time limit. So let's move on to the next problem, D. So yet another array problem. You are given an integer n and an array A of length n. Find the smallest integer x such that an index I with GCD AI, x equal to 1. If no such x exists within the range this, output -1. and the constraints for this question is, for this problem is, n is still 1e5 and ai is still 10 to the power 18. And it is guaranteed that the total sum of n across all test cases does not exceed 1e5. So basically, because of this, the expected time complexity for this question would be now O of n or O of n log n. O of n square would not work because 10 to the power 10 operations will be too much. So let's see the test cases now. So this problem is, basically we are given an array A, and what we need to do is find the smallest integer x such that there exists an index I with GCD ai comma x is equal to 1. Find smallest x such that there is an index I with GCD ai comma x is equal to 1. So we need to find an x which is basically co-prime with any one of the numbers in the array. So let's see the test cases. Now the first test case is 1, and basically we need to find the x should be greater than 2 and less than 10 to the power 18. Obviously x cannot be 1, otherwise the answer for all the test cases would be just 1. So the first test case, the answer could be anything, since 1 is co-prime with every other number. So basically I don't know if it is co-prime because the properties might be different for 1, but GCD of 1 with any other number will be 1. So the smallest possible number would be then 2. Now the next test case is 6, 6, 12, 12. Let's see that. 6, 6, 12, 12. So let's try to naively find the answer, right? So x can be anything from 2 till 10 to the power 18, right? So let's check if 2 can be the answer. So obviously 2 cannot be the answer, since all of these will have a GCD of 2 with 2. Basically GCD 6, 2 is also 2 and GCD of 12, 2 is also 2. So 2 cannot be the answer. Moving on, let's check for 3. So again 3 also cannot be the answer because all of these have 3 as a divisor. Then 4. Again 4 also cannot be the answer because GCD of 6, 4 will be 2 and GCD of 12, 4 will be 3. So 4 also cannot be the answer. Checking for 5. Yes, 5 can be the answer because GCD of 6, 5 is 1 and GCD of 12, 5 is also 1. So one observation that we can make here is, so we checked for 2, we checked for 3, we checked for 4, we checked for 5, and 2 was not possible, 3 was also not the answer, 4 was also not the answer, and 5 we got the GCD as 1. So 5 was the answer. So basically one thing I can say from this test case is, one observation that I can make, I saw that 2 and 3 both did not satisfy the condition of the answer. 2 and 3 both did not manage to satisfy this condition. So do we really need to check for 4? Because 4 has 2 as a factor. And if 2 was not co-prime with any of these, 4 will also not be co-prime with any of these. Since 2 was not co-prime with any of these, then obviously 4 will also not be. Or more generally, any multiple of 2 will not be co-prime. Because if 2 is not co-prime, then that means every number has a factor common with 2, and every multiple of 2 will also have that factor in common. So any multiple of 2 cannot be the answer. And similarly, now we can generalize this more. Since we can say the same thing for 3 also. So basically, if 3 did not satisfy the condition, any multiple of 3 will also not satisfy the condition, right? We can say that for 3 also. So more generally, the answer will only be 1 or a prime number. Actually 1 cannot be the answer. So the answer will only be a prime number. Because we checked for 2, then we checked for 3, we obviously don't need to check for 4. And the next number that is not divisible by either of 2 and 3, that will be the next prime number, 5. Now the next number is 6, we don't need to check for 6 since 2 and 3 we already rejected, right? 7 we need to check for 7 since it's a new prime number. 8 again we don't need to check. 9 we don't need to check. 10 we don't need to check. 11 we need to check. Since 8 again 2 has a common 2, 8 is a multiple of 2, 9 is a multiple of 3, 10 is a multiple of 5. So if we checked for 5, 7 and 11, we don't need to check for these numbers. Since obviously if 10 was an answer, 5 will also be an answer, because 5 has because 10 has all the factors that 5 has, and even then if 10 managed to be co-prime with some number, 5 will also be co-prime with that number. So we only need to check for the prime numbers. So let's write that. We only need to check for prime numbers. Right. So let's see further test cases. So the next test case is 24, 120, 210. 24, 120, 210. So again, let's now since we made this observation, so let's make use of that. So let's start by checking with 2. So obviously all of these numbers have 2 as a factor, so the answer is not 2. Then let's start by checking 3. So again 3 is also a factor of all of these numbers, so let's start now. Let's check for 5. So 5 is not a factor of 24, so GCD of 24 and 5 will be 1. So 5 is the answer. Again another thing that I can see from this is, if I follow this property, I can say that GCD of AI comma x, where x is a prime number. So GCD of AI comma x can only be 1 or x. Since x does not have any divisors, so GCD of AI comma x will always be 1 or x. So basically, if there is a single number that is not a multiple of x in the array, then x will be the answer. So basically I need to check whether the GCD is 1 or not, right? So the GCD is x only when AI is a multiple of x. When AI is a multiple of x, the GCD is x, else it is not. So what I need to do is, we need to find the smallest prime number which has at least one corresponding AI which is not a multiple of that prime number. So since 5 was the first prime number here that had 24, which is not a multiple of 5, so 5 will be the answer. And the next test case, we have 2, 4, 6 and 10. So 2, 4, 6 and 10. Again we check for 2. Obviously all are multiple of 2, so 2 is not an answer. We check for 3. 2 is not a multiple of 3, so GCD of 2, 3 will be 1, so 3 is the answer. So that's how we can do. So now we cannot simply check for each prime number, right? We cannot simply do that. So what we need to do is, we cannot check for each prime number by iterating over the full array, because that would be a n square time complexity. So what we need to do is, we need to find some clever way of finding the smallest prime number that has a number which is not a multiple of that prime number. So what, let's take this test case, 6, 6, 12, 12, 6, 6, 12, 12. So we see that 2 has all the numbers are multiples of 2. We see that all the numbers are multiples of 3. And we see that 5 does not have its multiple, right? 5 has a number that is not its multiple. So basically what we are doing here is, we are finding numbers which are factors of all the numbers. So basically 2 and 3 were factors of all the numbers, and the next prime number 5 was not a factor. So 5 was the answer. So basically if we know that what prime numbers are factors, then we will just take the next prime number and that will be the answer. So this is a well-known thing, finding numbers which are factors of all the numbers. So this is nothing but GCD. This is very close to actually calculating the GCD of all the numbers. Since let's take the GCD of 6, 6, 12, 12, and we get 6 as the GCD of 4 of these numbers, and 6 has the factors 2, 3, and it does not have the factor 5. So basically, since it does not have the factor 5, what does that mean? That means that there must be at least one number in these that is not a multiple of 5. So if there is at least one number in these that is not a multiple of 5, then GCD of all these numbers will not contain the factor 5. So what we can do is, we can, instead of solving the original problem, now we can reduce this to this problem. Find the smallest prime number which is not a factor of GCD. Of the array, of the full array. So basically now let's denote the GCD of the array as G. So we can obviously represent any numbers in its prime factorization form, p1 to the power of a1, p2 to the power of a2 till pn to the power of an. we can obviously represent it in this form, where P1 is greater than equal to 2 and is prime, and Pi actually, and Ai is greater than equal to 1. So we can obviously represent any G in this form, and then we need the smallest prime number, which is not here, right? So here we know one property, that n must be less than equal to log G base 2. N must be less than equal to log G base 2. Why this property? Because let's say that all the AI are equal to 1. Let's just say that all the AI are equal to 1. So this will look like P1 into P2 till Pn. So since AI, we have reduced the AI to the smallest possible value, and we know that Pi's are all greater than equal to 2. So sorry, this inequality will be changed to G is greater than equal to P1 into P2 till Pn, and G is greater than equal to 2 to the power n, since P is also greater than equal to 2. So if we take log base 2 both sides, so log G base 2 will always be greater than equal to n. So this is simply n is less than equal to log G base 2. So log G base 2 is a very small number. Since in the question we are given numbers till 10 to the power 18, right? So G will be less than equal to 10 to the power 18, and log G base 2 will be less than equal to 18 log 10 base 2, which is somewhere around I think 4, so which is less than 80. This is a very far approximation, but yep, this number is less than 80. So n will be less than 80. N is nothing but number of different prime factors. Prime factors, yep. Number of different prime factors are less than 80. So what does this mean? Since the total number of prime factors are less than 80, right? So there must be at least one prime number which is not a factor of G in the first 81 prime numbers. So basically what I am saying is, in the first 81 prime numbers we will always find the answer, because the total number of different prime factors of G are less than equal to 80, right? And since the number of prime factors are less than equal to 80, out of 81 different prime numbers, one must not be present here. At least one must not be present here. So, and since we need to find the smallest prime factor that is not present here, so that will solve the question. So we only need to check for first few prime numbers and we will find the answer there. So that is it. So what we can do is, we can simply find out G. To find out G, we can just use a simple for loop. For I equal to 0, I is less than n, I plus plus, and G is nothing but GCD of G comma AI. So this is it. And then what we can do is, for P in prime numbers, if G percentage P is not equal to 0, is E not equal to 0, then answer equal to G and break. Answer equal to P and break. Now we need to know the first few prime numbers for this, and for that we can actually either find them online and hard code the prime numbers, or what we can do is, there is an algorithm known as sieve, which lets us find all the prime numbers till n in O of n time complexity. So if you guys don't know about sieve, you guys can go and check it out first. I'll here just briefly explain how that works. So I'll just take n equal to 20 and dry run the sieve algorithm. So what sieve algorithm does is, let me just write out all the numbers: 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So let's remove 1. So we know that 2 is a prime number, right? So all the multiples of 2 cannot be the answer. So 4, 6, 8, 10, 12, 14, 16, 18 and 20 cannot be the answer. Now again we know that, so 2 is now fixed to be a prime number. Now 3 is a prime number. So any multiple of 3 cannot be the answer and cannot be a prime. So 6 is not prime, 9 is also not prime, 12, 15 is also not prime, 18, 21. So now we fix 3 to be prime. Since we have already cut out 4, that means 4 is not a prime number. So the next prime is 5. Now we need to remove the multiples of 5. So 10 is already removed, 15 and 20 is also removed. So 5 is now the next prime. 6 we have already cut out, so 7 will be the next prime. 7 multiples already all have been cut out. Then 11, then 13, then 17 and then 19. So basically that is how sieve works. Basically we are, for every prime number we will just remove all the multiples of it from the, we will mark all the multiples of it as composite. For every prime number we will do that, and in the end we will end up with all the prime numbers. And since for every prime number the loop will run n upon pi times, so the overall time complexity would be sum of n over pi, which will be n by 2 plus n by 3 plus n by 5 plus n by 7 and so on. And this approximates to log n. Actually not this. Let me take n common and this will become 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7 and so on. And this approximates to n log n. So the time complexity of this algorithm will be n log n. Oh, actually I made a mistake here. This is O of n log n. And in O of n log n we will find all the prime numbers. So you guys can go and check this algorithm out. I just briefed it here. I'll not be showing the implementation. You guys can implement on its own. I'll link my implementation in the description. So that is how we can find the prime numbers. So we can just run sieve till something like 1e7, that obviously has a lot more prime numbers than 80, and then simply follow this for loop to find the answer. So I'll show you guys the code. So better sieve is a function that runs that sieve and will give me all the prime numbers till 1e7. And so I have done this pre-calculation, so this will not be included in the overall time complexity for each test case. So this is separate, and then simply I have taken the input v, vector v, and then I have found out the GCD of the whole array. And then I'll simply just brute force. I'll simply check for all the prime numbers starting from 2, and the smallest prime number that is not a factor of g, that will be the answer. So I'll just see out that and break, and obviously I'll find the answer before 80 prime numbers. So this for loop will run a maximum of 80 times, and then obviously the time complexity for each test case would be just O of n only, because this is this can be considered as constant only. So O of n time complexity with O of 1e7 log n pre-calculation. So that was the solution for problem D. Let's move on to problem E. So Kahba has n friends, each standing on a line at position ai, and each of them is in the range 0, x. They all want to come to him. One of his friends, Ismatadin, gave him k teleports. Each friend will walk to the nearest teleport, choosing the shortest distance. Once a friend reaches a teleport, Kahba and the friend can instantly meet. but Kirba is so tired that he'll be sleeping while his friends are walking towards him. Now he wants to choose k teleport positions so that their positions are distinct and lie within the range 0, x. In order to maximize the time it takes for the first friend who reaches a teleport to reach it, assume that friends move at the same speed. Since Kirba isn't good at calculations, you should output the k chosen teleport positions. Just a second, guys, I'll come back from the washroom. Okay, so and the and the constraints for this, I'm recording, right? The constraints for this problem is t is till 10 to the power 4 and n and k are till 10 to the power 2 into 10 to the power 5, and x is greater than n, x is greater than k minus 1 until 1e9, and the second line of each test case there are so guaranteed the sum of n overall test cases does not exceed 2e5 and sum of k overall test cases does not exceed 2e5. So because of this, the overall time complexity expected would be O of n log n or O of k log k and or something like that, n log n plus k log k, anything like that will work. Basically O of n and O of k for loops will work, and log n complexity at max other than that, because n square or k square will not work. So let's see. Problem E. So basically we are given positions of n friends and the number of teleporters that we need to place, and k is the range where we can place the teleporters. We need to place k teleporters between n friends such that the first friend to reach a teleporter will take the maximum time. And we are given that all of the friends move at the same speed. So basically, in other words, we can say that the question wants us to maximize the minimum distance of a teleporter from any friend. So we just need to maximize the minimum distance of the teleporter to any friend. Right. So let's see the test cases. The first test case is the friends are at 1024 and we need to place one teleporter in range 0 to 4, right? 0 to 4. So let's make a number line that will help us visualize this better. So this is the number line 0, 1, 2, 3 and 4, and we have friends on 0, 1, 2 and 4, and we need to place just one teleporter. So if we place the teleporter here, then obviously this friend will make it to the teleporter in 0 distance. So the minimum distance would be 0. If we place it here, again the minimum distance would be 0. If we place it here, the minimum distance would be 0. If we place it here, then the minimum distance will be 1, because this is 1, and then all the others are greater than this. So, and if we place it here, then again it will be 0. So this will be the optimal placement. So 3 will be the answer. 3 will be the answer. Okay. So the next is 0, 1, 2, 3, 4. And the range is still 0 to 5. 0, 1, 2, 3, 4. Range is still 0 to 5, and we need to place 5 teleporters. So if we need to place 5 teleporters, then obviously one of the teleporters will be on these, and that will make the minimum distance as 0. So it doesn't really matter how we place them, the minimum distance will be 0 only, right? So we can just simply place them like this, the 5 of these. So that way, that 0, 1, 2, 3, 4 will be the answer for this. The next test case is 4, 0, 0, 4. And the range is again from 0 to 4 only, and we need to place one teleporter. So let me make the number line better. 0, 1, 2, 3, 4. So if we place the teleporter here, then the minimum distance will be 1. If we place it here, minimum will be 2. If we place it here, minimum will be 1. So we can place the teleporter here, and the minimum distance will be 2, which is the maximum possible. So the answer will be 2 in this case. So the answer is 2. So the next test case is 2, 4, 3, and we can place till 6. So 0, 1, 2, 3, 4, 5 and 6, and the friends are at 2, 4, 3, 2, 4, 2, 4 and 3, and then we need to place 4 teleporters. So 4 teleporters, right? So obviously if I place the teleporter on any of the friend, then the answer will be 0. So this will be the placement, and the minimum distance will be 1. So this will be the placement, 0, 1, 5, 6, 0, 1, 5, 6. So basically what we need to do is we can follow this very naive process. We can let's maintain a array distance 0, 1, 2, 3, 4, 5, 6 and so on till infinity. And what this distance array is, we can start from here only, and we can see if we can make the minimum distance as 0 or not. So if we can make the minimum distance as 0, we move on to the next. If we can make the minimum distance as 1, we move on to the next. If we make the minimum distance as 2, we move on to the next. And wherever we can't make the minimum distance, so let's say we cannot place the teleporter such that we can make the minimum distance of the teleporters to any friend as 3. We cannot do that. So then the answer would be 2, because that is the maximum possible minimum distance. So that way we can do. So just simply checking over each of the values would take a lot of time, right? Obviously we cannot check over infinite values. So what we can do is we can make use of binary search. And what this will do, since if we are searching in a range 0, 1, 2 till n, so what we can do is we can simply check for the n by 2 value. If we can find an arrangement that makes the minimum distance as n by 2, then obviously all the smaller distances will obviously be possible, right? Let's take one simple example. Let's take 0, 1, 2, 3, 4 and 5, and let's place the friends here. So if I place and let's say that I only have one teleporter to place, and if I place my teleporter here, the minimum distance will be 2, right? So what I can do is I can simply move my teleporter here and the minimum distance will now be 1, and if I move the teleporter here, the minimum distance will now be 2. So if minimum 0. So if there is an arrangement where the minimum distance possible is 2, then there are arrangements corresponding to minimum distance 1 and 0 as well. So we don't really need to check for the shorter numbers, smaller numbers. If n by 2 is possible, then we only need to check for the answer in this range. And then again we can take the mid and see if there is an arrangement possible for this value or not. And if it is possible, if it is not possible, then our range will shorten like this and we will converge towards the answer in only log n operations. So we can do this, we can use the binary search because of this property, because of the property that if there is an arrangement that gives minimum distance as x, then there will always be arrangements possible for minimum distance less than x, and another property is that if arrangement is not possible for x, then it is also not possible for distance greater than x, because obviously here we can see that distance of 5 is not possible, then obviously 6 will also not be possible there, because if we are not able to make the minimum distance as 5, then obviously we will not be able to make the minimum distance as 6. So because of these two properties, we can apply binary search in this question. Now all that remains is for us to write a check function. We need to now design a check function, a function which will tell us whether a distance is possible or not. So how we can try to think about how we can write this check function. So let's take a number line. So on this number line there will be some friends, right? Some friends. And we will be having to place teleporters here. So let's try writing the check function for the minimum distance as val. Let's take this variable val, which is the minimum distance that we are trying to write the check function for. So here will be 0 and here will be x. So obviously below the first friend, what we can do is if this index is a1, a0, let's mark these indexes as a1, a2, A3, A4. Okay, so basically what we can do is, here is 0, here is A0, and somewhere in between there might be A0 minus val. So what we can do is, we can place teleporters all over this range. In this range we can place teleporter anywhere, and that teleporter will be away from all the friends with a distance greater than val, because the nearest friend will be A0, which is having a distance of val from any of these teleporters, which is having a distance of greater than val from any of these teleporters. So we can place a teleporter anywhere in this range. Actually, A0 minus val might be less than 0. It might come here. So in that case, we will not be able to place any teleporters, because this value is already gone below 0. So we can place the teleporters from 0 to A0 minus val. We can place from 0 to A0 minus val. This is one way we can place, and again similarly here also we can do the same procedure, and we can place from A4 plus val to X. These two ranges we can place the teleporters on all the points. Now the range that remains to check is this much. So basically between the friends, right? Wait a second. Where did that go? I'll just make it again. I'm sorry. So basically, let's say we have friends here, A0, A1, A2, A3, A4, and we have X here and 0 here. So we found out that we can place from 0 to A0 minus val, and we can place from A4 plus val to X. In these ranges we can place the teleporter anywhere, and that would be further from any friends more than a distance of val. So here we can place, and here we can place. Now we need to check for this range. So obviously if I am placing between these two friends, I need to just worry about the distances from these two friends, because if the distances from these two friends is greater than val, then obviously from all the other friends it will be greater than val. So I just need to focus on the two friends, right? So let's just take an arbitrary ai and ai plus 1, and let's find out the possible different points that I can place the teleporters in this range, and then we can similarly use that in all four of the segments, all four of these, 1, 2, 3 and 4. So let's just try to find from ai to ai plus 1. So what we can do is, we can start placing from ai plus val, and we can place teleporters till ai plus 1 minus val. So basically we can place the teleporters from ai plus val to ai plus 1 minus val. So these three types of ranges we can put the teleporters anywhere on, and if these set of points have more than k points, then the check function will return true, else false. Basically, if these there are more than k points in these set, then obviously we can select any k out of those, and that will be a possible arrangement for the minimum distance to be greater than equal to val. Val is basically what we are writing the check function for. So k points. So check is true and check is false, and we can simply select the. So we can just do this in O of n, since we need to just simply add the number of points here, number of points here, number of points here, and see if it is more than k. And we can do this in O of n because there are only n ranges, n plus 2 ranges actually, n are here and 1 and 1. So we can do, and that will be our check function. So our check function is O of n, and we have our binary search, which is O of log n. So overall time complexity would be O of n log n, which is good enough for this question. So I'll show you guys the code. So basically I take input v and I sort it, and I'll show you guys the check function first. So let's understand the check function. So set S is nothing but the set of points that I'm going to choose, okay, and these are the ranges. V of I minus V of I minus 1 is this range, basically these. So obviously for any point to lie in this range must be like this, right? Ai plus val must be less than or equal to ai plus 1 minus val. So ai minus ai plus 1, sorry, ai plus 1 minus ai should be greater than equal to 2 into val. So that condition I have written here, vi minus 1 should be greater than equal to 2 into val. Then I can just run a for loop from this point to this point. So the first is v of I minus 1 plus val, basically ai plus val, and v of I minus val, basically ai plus 1 minus val. I have in my code I have done it like this, I minus 1 and I, a. So I have done from ai minus 1 plus val till ai minus val. It is essentially the same as this. So first the starting point will be this and the last point will be this. So what I can do is I can run a for loop from the first point till the last point while position is less than equal to k and temp is less than equal to last. So what I will do is I'll insert all the points in the set. S dot insert temp. Temp is nothing but a variable running from first till last, and I'll just keep on inserting it in the set while, and this is nothing but if the temp is a position where I can place a teleporter, right? So if I have not already included it in the set, then I will add it in the pause vector. Pause is nothing but the positions where I can place the current teleporters on for the corresponding to the value val. So in pause I'll push back temp and I'll insert the temp in the set and temp plus plus, and this line actually does not matter. I changed it further in the code. Count is nothing but pause dot size, so just ignore this line, it will not affect. And so this was these ranges, and then I need to do for these two ranges also. So the first will be 0 till v of 0 minus val, 0 till a of 0 minus val, and then again same, I'll just run my variable temp from first till last and see if the variable temp is not already in the set S. If it is not in the set S, then I will just push back in the pause vector and insert it into set. Similarly from vn minus 1 plus val till x, again I'll run the for loop. So this might look like n square complexity because I am running a for loop of O of n here, and then again inside I am running a while loop which might be O of n. So this might look like O of n square, but since I have this condition, pause dot size is less than equal to k, so this while loop must run at max of k times only, because in each iteration of this while loop I am inserting a position in the inserting a value in the pause vector. This condition will be true most of the times, it will only not be true in cases where val is 0 or something like that, because see, if I am finding the points between these two friends, these all points will be unique, right? Only these 2 points can be overlapping in the next range. This point might overlap with the next range, but these points will always be unique for all the 2 friends. So I am always adding unique points only. So this condition will only be true when I am trying to add this point, which is only when val is equal to 0. So this condition will not hit much, so don't care about that, and just think of it as like in each iteration of this while loop, I'll push backing one element to the pos vector. So these while loops will run a maximum of k times only. All these while loops will run a maximum of k times, because pos size will not be going higher than k. So the overall time complexity would be O of n plus O of k, and log n complexities, O of k log n and O of n log n. So that this whole check function would be of around O of n log n plus k log n type of complexity. And then I have the binary search, which is nothing but I am finding the answer between the range 0 to 1e9, and then I am checking for the mid value. If the check function is false on the mid value, that means I cannot form an arrangement where the minimum distance is greater than equal to mid. So that must mean the answer will lie between L and mid. So I am setting R as mid, else I will set L as mid, because the answer will be greater than L. And then in the end I will just whatever positions I have calculated, I will see out them. Yep. And here in this else, I am again running this check of else, so that this pos vector will be updated. So that was the code for problem E. So let's move on to the next problem. So Behrusbek received a tree with n nodes. For a chosen root R, Behrusbek wants to find cuteness of the tree. Consider every set of k distinct nodes of the tree. For each set, compute its lowest common ancestor LCA in the tree when it is rooted at R. Let SR be the set of all distinct nodes obtained this way. Then cuteness of the tree's SR, size of SR, where this means the number of distinct elements. After discovering the cuteness of the tree, Behrusbek became interested in finding the kawainess of the tree. Kawainess is defined as sum of all the sizes of SI. Unfortunately, Behrusbek is feeling sleepy now. Please help Behrusbek by finding the kawainess of the tree. And the constraints are n is till 2e5 and k is also till 2e5, and sum of n does not exceed 2e5. So again, the expected time complexity in this question also will be till O of n or O of n log n. So okay, they are still in queue. Okay, so problem F. Basically, let's define the cuteness. So cuteness of tree SR. So what is this? Basically, the root is fixed to be R, and then what we can do is the count of cuteness is equal to the count of nodes which are the LCA of k different nodes, k nodes in the tree. So basically what this is, we can we can choose any k nodes from the tree, and if the LCA of those k nodes is a node, then we need to count the number of such nodes which are the LCA of k nodes. Let's take some example and we will understand better from that. So let's make some tree 1 2 3 3 4 5 6 7 8 and 9. So this is the tree. Let's take k as 3 and let's try to find S1, cuteness of S1. So let's denote the cuteness of S1 as this. So when the root is 1, so the root is 1 and now we need to find the cuteness, right? So basically we need to find the number of nodes which are LCA of 3 nodes. So can 1 be the LCA of 3 nodes? Yes, obviously we can select these 3 nodes and these 3 nodes will have the lowest common ancestor as 1. So 1 is possible, 1 is inside the set. Now can 2 be a possible node? So yes, I can select these 3 and yes, 2 will be a possible node. Can 3 be a possible node? Yes, I can select these 3 and 3 will be a possible node. Can 6 be a possible node? No. There are no 3 nodes that I can select which have an LCA of 6. Can 5 be? No. So 5 is also no, 6 is also no, 9 also no, 7 also no, 8 also no, 4? Yes, 4 can be a possible because we can select these 3 and yep. So basically, obvious observation that if a node has greater than equal to k elements in its subtree, then that node is good. We can see that we can look at this 3. This 3 had this subtree and it had 3 elements which is greater than equal to q, which is greater than equal to k, then so it was cute. Basically, we will let me just generalize this a little bit. Let's say that I have some node x here and this is its subtree. So what I can do is I can select this node and I can select k minus 1 nodes from its subtree, k minus 1 nodes. So this will be a total of k nodes that I have selected, and obviously all these k nodes will always have the LCA as this node only, because all the nodes are selected from its subtree, and so the ancestor of this node will somewhere lie in the inside of this subtree only, and if I take the LCA of that and this node, then the LCA will always be this node only. So if a node has greater than equal to k elements in its subtree, then that node is good. So basically, cuteness is nothing but count of nodes with greater than equal to k nodes in its subtree. Right. So now now since we know how to calculate the cuteness, let's see the test cases. First test case, let's leave that. Let's move on to the next test case only. Actually, let's take this test case. 1 2 1 2 1 3 2 4 2 5 3 6. Okay, so this is the test case. Just a second. So let's find S1 here. So what will S1 be? 1 has a lot, 1 also what is k? K is 3. So for 1 we can select these 3. So 1, 2 also is good, 4, 5 are not good, 3, 6 are not good. So S1 is 2, right? Also let's just write the number of elements in the subtree. 1 2 3 4 5 6 in for 1, for 2 it's 3 1 1, then 2 1. So we can see that only these two have greater than equal to 3 elements in its subtree. So now let's find S2. Let's find S2. So let's root the tree at 2, 2, then 4, 5. Then we have actually let me 5 and 1 and 3 and 6. So again let's write the number of elements in the subtree: 6 1 1 3 2 1. So again 2 elements, so S2 is also 2. Now let's root the tree at 3. Let's just complete this process once and let's then make the observations. So let's root the tree at 3, and one of the child will be 6. Let me just do it like this: 6, then 1, then 2, then 4, 1 2 4 and 5. Okay, 3 6 1 2 4 and 5. Okay, so 6 1 4 3 1 1. So now we have 3 elements which have greater than equal to 3 nodes in its subtree. So S3 will be 3. Let's root the tree at 4. So 4, then 2, then 2 is connected to 5 and 1 is connected to 3 and 6. So 6 1 2 3 4 5 1 3 2 1. So again 3 nodes have greater than equal to 3 elements, so S4 is 3. Let's root the node at 5. So 5 and 4 are symmetrical, so we can just, it will be same. Again 6 5 3 2 1 4 1. So again 3 nodes, so S5 is also 3. Now let's root the tree at 6. 3 1 2 4 5. So 6 5 4 3 1 1. So now we have 4 that are greater than equal to 3, so S6 is equal to 4. So we can total them. 2 plus 2 4 plus 3 7, 7 plus 3 10, 10 plus 3 13, 13 plus 4 17. The answer for this test case is 17. So basically let's try to first solve this question naively. Okay, so what we need to do is we need to root the tree at all the from 1 till n, and then we need to find the number of elements in the subtree of each node. So our first problem currently is how do we find the number of elements in each subtree. Okay, so this is a very common problem in CP and it has a very easy solution using a little bit of dynamic programming. So basically what we are trying to do here is, let's say that in some tree during the DFS we are on some node P, and then we will from here go on to the node C and nodes child of this P, C1 and C2. So basically the subtree of P will be nothing but subtree of C1 plus subtree of C2 plus 1. So this is nothing but the sum of the childs the sum of the number of nodes in the child subtree plus 1. So let's make a tree. Okay. So how do we calculate the number of elements in each subtree? We do it like this. Basically the leaf nodes will all have the answer 1, right? Obviously. And now for 2, the sum of its child 1 plus 1 plus 1. Basically sum of child, sum of subtree of child plus 1. So 1 plus 1 plus 1, 3. Again here from 8 we can calculate 7, which will be 2. From 6 and 7 we can calculate 5. 3 plus 1, 4, and from this we can calculate for 1. So this is how we can calculate the number of elements in all the subtree. And this is an O of n solution because we are using dp here, and in code it will look like this. We can do a DFS simple. And what we can do is, for child of node, we can just run DFS on them, and once we have run the DFS on them, we know that the values of child are calculated. So subtree of node will be plus equal to subtree of child, and subtree of node initially will have 1 element. So this simple code will give us the subtree, the count of nodes in each subtree. So now what we have designed is, we have designed an n square solution. Basically what we can do is, we can root the tree at every node, then we can run this DFS to find the subtrees of each node, and then we can count the number of subtrees which have greater than or equal to k elements. So that will be all done in O of n for one given root, and then to calculate for all the roots we will run an O of n square loop. But this is not allowed for this question. We need to solve it in O of n. So we need to optimize this, right? How can we optimize this? Let's look at this. Let's look at how we calculated this. Okay. So initially we had this tree. But then we shifted the root from 1 to 2. Okay. We shifted the root from 1 to 2. So what happened? We can see that 3, 6, 5 and 4, all the other nodes except 1 and 2 remained the same. Basically subtree of 3 will still have 2 elements. Subtree of 3 will still have 2 elements. Subtree of 6 will still have 1 element. Subtree of 5 and subtree of 4 will also have the same elements, because simply we are shifting the root. In the subtree of these nodes nothing will happen. They will remain the same only. So, and similarly we can see when we go from 2 to 4. See, this is the root at 2, this is the root at 4, right? So we can see that all the nodes except 2 and 4 are same. 5 still has 1, 1 still has 3, 3 still has 2 and 6 still has 1. Only 2 and 4 changed. Basically let's look at this like this. So there is a parent and there is a child, and there is subtree of this child and there is subtree of this parent. Now what happens when we make this child as the root? So let me not write this as P, let me write this as R. So what will happen when I make this child as a root? This will look like this. So child, then root, then the children of root, basically this, and these will come here. So all of these remained fixed only. All of these subtrees remained the same. The only subtrees that changed were the original root and its child, and now the new root and the last root. So what we can do is, if we know the answer for this tree, we just need to update the values of these two for the new tree. We don't need to again check whether these subtrees have a value greater than or equal to k or not, because these subtrees are already the same. We don't need to recalculate this. Okay. So let's take an example here. Right. So when 1 was root and when 2 was root, let's look at this. So when 1 was root, these four, nobody was greater than or equal to 3, and again in the next also when 2 is root, no one will be greater than or equal to 2, greater than or equal to 3. So we just need to update for 1 and 2, right? So can we do it in some way where we don't need to run another DFS and calculate all the subtrees? We need to find out, we need to actually do this transition from this to this in O of 1, right? We are currently calculating the answer for all the roots in O of n, but we need to do it in O of 1 because O of n square is not allowed. And we see that we are recounting a lot of things. We see that we are recounting these. We don't actually need to recount these, right? So now let's try to formalize. So let's say that the answer for this corresponding for this tree was let's say dp of r. Okay, for this tree the answer was dp of r. Now if in some way, now if we can find the answer for this tree using this dp of r in O of 1, then our problem will be solved. That was the whole issue. So we don't want to calculate this in O of n. We need to do it faster. So if dp of r is known, let's try to find out the value of this. So let's say that the subtree of C initially had k elements. Actually, what variable have I used in the code? Let me see. So x. So initially let's say that the subtree of C had x elements. So this will be n minus x remaining elements, right? And now we can see that in the new tree, R will now have n minus x elements and C will have n elements in its subtree, where C previously had x elements and R previously had n elements. So the only changes that were made are subtree of R went from n to n minus x and subtree of C went from x to n, right? And we are given that k is always less than equal to n. We are given that in the question. See, k is always less than equal to n. So from the original dp of R, what we can do is, if n minus x is less than k, what happens when n minus x is less than k? So basically, initially n was greater than k, but after we changed the roots, n minus x became less than k. So basically, this node was a good node initially, but after we changed the root, it became a bad node. So in this case, we will have to subtract by 1. And what happens if x is less than k? So if x is less than k, then initially this was not a good node, but in the after case it became a good node. So here we will actually this is not correct to write it like this. We will do a minus 1 in this case and a plus 1 in this case. So basically let's make a difference variable, difference 0, and let's update that variable here, difference minus minus and difference plus plus, difference minus minus and difference plus plus. So this, and now the dp of C will just be equal to dp of R plus difference. So if we had known the answer for dp of r, we calculated the answer for when the tree is rooted at c in just O of 1. So that is a good thing for us, right? So let's make a new tree. Let's just try to apply this on a tree, and then after that I'll show you guys the code. So you guys must have understood how we are transitioning, and you'll better understand when I do it on a tree. So let's again take that tree only, 1 2 1 3, 1 2 1 3, 2 4 2 5, 2 4 2 5 and 3 6. Okay, so initially we will just simply run a for loop. We will simply run an O of n loop to find the answer for when tree is rooted at 1. So this will be 6, this will be 3 2 1 1 1. So answer will be nothing but 2. So S of 1 is nothing but 2, or actually let's denote this as dp of 1 is nothing but 2. Okay, so now let's calculate from 1. We saw that in our dp that we can calculate from dpr the answers for its child. So from 1, let's try to find out the answers for 2 and 3. So in case of let's find out dp of 2. So here x was the number of nodes in the subtree of C, right? So x is equal to 3. Now we need to check for these two conditions. If n minus x is less than equal to k, so if 6 minus 3, 3 is less than k, or if x was less than k, which is 3 was less than k is also 3, right? So here we will difference minus minus, and here we will difference plus plus, and since both of these conditions are not true, so difference will remain 0, and dp of 2 will be equal to dp of 1, which is nothing but 2 only. Now from 1 we can also calculate 3, and dp of 3 we can calculate. So for this, x is now 2 because number of elements in 3 subtree is 2. So if n minus x, which is 4, is less than 3, then we do difference minus minus. If x is less than 3, then we do difference plus plus. So now this condition is true, so we add 1 in dp2. So dp3 will be 2 plus 1, which is 3. We can cross check also. S1 was 2, S2 was 2, S3 was 3. So now we have found out the answer for this, this and this. Let's move on to finding the answer for these. So again we know the answer for 2, and we are trying to find the answer for 4. Here the value of x will be equal to 1. So again, since x is 1, n minus x will be 5. So n minus x is not less than k, but x is less than k because 1 is less than 3. So x is less than k, we add plus 1. So dp of 4 will be dp of 2 plus 1, which is 3. Similarly, dp of 5 will also be 3, and dp of 6, again x is equal to 1 and x is equal to 1, so we will add 1. So dp of 3 plus 1 will be the value of dp of 6, which is 4. So the overall answer will be nothing but sum of dpi, which is dp1 was 2, dp2 was 2, dp3 is 3, dp4 is 3, dp5 is 3, dp6 is 4. So 4, 7, 10, 13, 17. So that is how this process will work, and I hope you guys understood how exactly I am calculating from dpr the value of dpc. dpi is nothing but the answer when the root is I. So that was the solution for problem F. I'll show you guys the code. So I am creating a graph For that I am maintaining this adjacency list, and sub t will give me the number of nodes in its subtree. Visited is nothing but a variable for DFS, and answer is nothing but our DP. So this is, I am resetting it for the current n, then I am taking input the graph, and then this DFS is to calculate the values of sub t. So this is nothing but vis of node is equal to 1, then I do sub t of node is equal to 1, and then DFS of child and sub t of node plus equal to sub t of child. So this will calculate the subtrees, number of nodes in subtrees for each node, and then what I can do is calculate the value of answer 1. We can just count the number of count the number of nodes where the subtree has more than k elements, so that would be answer 1, and then I can reset the visi to 0 for my next DFS. So the next DFS will use this answer 1 to calculate all the other answers. So what we will do, vis of node 1, and from node we will find the value of all its children. So x was the number of nodes in subtree of child, and difference is that difference variable. So if n minus x is less than k, difference minus minus. If x is less than k, difference plus plus. And answer of child is equal to answer of node plus difference. So from this we will have calculated the value for the child node, and then we will, in the further DFS call, we will calculate the answers for the descendants of this child. So this is how our DFS2 will work. So after DFS2 we can just take sum of all the answers for all the roots, and then that would be the final result. So both of these DFS are O of n, and the whole problem was, so the total time complexity would be O of n only. So that was the solution for problem F. Let's move on to the problem G. So Muhammad Ali has an integer array a1 till an. So he can change any subset of positions. Changing position I costs ci and replaces ai with any integers of his choice. The position that he does not change must retain their original values. After all changes, we call an index I a drop if the final value at position I is strictly greater than the final value at position I plus 1. Muhammad Ali wants the final array to contain no drops. Find the minimum cost of changes required to ensure that there are no drops in the array. And the constraints for this problem is t is given till 5000, n is given till 8000, ai and ci are both till 1e9, and the sum of n across all test cases does not exceed 8000. So the expected time complexity could be O of n square, because 8000 square would be 16 into 10 to the power 6, which will run fairly easily in 1 second, because the maximum limit is 10 to the power 8 operations. So n square would be the expected time complexity. So problem G. So basically we are given an array A, and we can perform some operations, array A and array C. We can perform the operations, which is basically change element ai to any other element with cost ci. So we can pay a cost of ci to change ai to any other element, to any other integer, and we need to use these operations and find minimum cost to make the array increasing. This increasing is not strictly increasing, it is greater than equal to, basically in ascending order. Okay, so find minimum cost to make the array increasing. So That was the question. The expected time complexity is O of n square. So now let's see the test cases. So the first test case, it's only one element, so don't really need to do anything. The next test case, it's already in ascending order, 1, 2, 2, 3. So again the cost is 0. The next array, 4, 3, 2, 1. Let's see for that. 4, 3, 2 and 1. This is the array A and the array C, 1, 1, 1, 1. So let's try to find the answer for this. So there will be two cases, right? There will be two cases that either I perform the operation on the first element or I don't perform the operation in the first element. So in the case where I perform the operation on the first element, I will obviously change it to be minus infinity, right? Because I need to make it increasing, so I'll make it just as small as I can make it. So I'll just do it minus infinity, and the rest will remain the same, and this will require me a cost of 1. Or if I don't want to do this, then I will just let it be like this, and the cost will be 0. Now in the case where I have already made the first element infinity, minus infinity, now again I will have two choices. Either I can change the second element, or I cannot change the second element. So what if I change the second element? Then obviously again I will make it minus infinity, and that will require me another operation. But what if I don't want to change? Then it will remain like this only. Now here comes the interesting part. Here also I have two choices. Either I can change 3 or I cannot change 3. So if I don't change 3, that will not be possible, because 3 is smaller than 4. I will obviously have to change 3. So I will have to do the operation on 3. And so after the operation, obviously the only operation that I will do on 3 is make the 3 4, because any greater than 4 and that I am doing, I don't really need to do that. I need to let the numbers be as small as possible so that the further numbers don't really have a problem. Basically that is the greedy choice that we can make here. Obviously transforming this 3 to 5 will not be beneficial. What if there was a 5 here? Let's say I transform this 3 to 6 and the next two elements were 5, 5. So obviously we should not be transforming this 3 to 6, right? We can make them 4, and if the next two elements were 5, we were done. So making them as small as possible will be the better choice here. So 4, 4, and then again also on 2 I will have to perform operation, and then again on 4, 1 also will have to perform operation. So the two operations would be 4, 4, 4, 4. And here also what if I decide to not do the operation on 3, because 3 is already greater than minus infinity. So I can choose to not do the operation on 3, and then I will have to perform the operation on 2 and 1 and make them 3. So this will be minus infinity 3, 3, 3. So in any case I will have to perform 3 operations. So the answer for this case is 3. So two things I would like to say. That first of all, the constraints, n square constraints. Okay, so this is one of the hint towards DP. Usually when n square and n cube are allowed, a lot of the times the solutions are DP. I am not saying every time, but a lot of the times. Now what is the other hint? While solving the test cases, we had to solve for both cases, take or not take. Basically we had to check for both the cases where we are performing the operation on a certain number or we are not performing the operation on a certain number. So this is again a very big hint for DP, because these types of problem are generally solved by DP, where we don't really make any greedy observations. We solve basically brute force every case. So again DP. Let's just move on to the let's see more test cases and then try to find a solution. So let's take this solution. No, let's take, okay, let's take this only, 3 1 2. So 100 1 1. So I have again two choices. I can either make this 3 minus infinity and use the 100, or I cannot change this. So obviously we see that this 100 is quite big, but so not performing, we are better off. We are better off not performing. But this is just an edge case because we had the number 100 here. But if we had a smaller number like 2, we would not be able to make such bold arguments. So we will have to check for all the cases. So let's just stick with checking all the cases. So let's make this 3 minus infinity, 1 and 2. So the cost of this operation will be 100, and this will be the final array because this is sorted now. So we can solve this on 100 cost. But what if we don't perform the operation? The array will remain 2 and the cost will be 0 only. Now obviously since this is 3, we will have to perform the operations on these two. So the array will become 3 3 3 and the cost will be 2. So the answer for this is 2. So we are seeing that basically, let's say we had some array, right? And let's say that we decided not to change this element, right? We decided not to change this element, and this element was a0. So now what will happen is I will have to make this element greater than a0, right? I will have to make this element greater than a0. If it is, so there can be three cases where this element, where a1 is less than a0, where a1 is equal to a0, where a1 is greater than a0, right? So in this case, I will always need to perform the operation and make it equal to a0, okay? In this case, I will never perform the operation because it is already a0, and a0 is the best possible value that can come here right now because this element need to be greater than equal to a0. In this case, we have two different routes that we can take. We can either make it a0 or we can leave it as a1. We can perform the operation here, or we can don't perform the operation here. So these are the cases that we need to handle. So basically what we can do is, we see that we either change, what if we had minus infinity? Basically if we had changed this element to the minus infinity, then this array would be our unique problem now, because this element now we don't really care about this element. So this array will be our new problem. We don't care about this element. We just add the operation cost of this plus whatever the minimum operation cost of this array will be. That will be the optimal value for when we change the 0th element. So how can we solve this problem? So we see that we are making choices. So we will have to use some kind of DP. Okay. And we can basically to find the answer for this array, the only value that you are concerned with is the last value, right? Last value is the only value that you are concerned with. Values before that we don't really care. So what we can do is we can define a state like this, I comma last. So what this will store is, this will store the answer from ith index till nth index, with last being the value at the last index. Okay, I minus 1. So now the way that we are performing the operations, right, the way that we are performing the operations, this last will either be minus infinity or equal to some value in the array, some value a, j, where j is less than I. Because either we are only copying the last value, right? If we are changing ai, then we are making it a0 or we are leaving it as a1. So the only possible values that can be on the last is minus infinity or some value aj where j is less than I. Some value aj where j is less than I. Basically, I think let's take 4, 3, 2, 1. 4, 3, 2, 1. So what happens if we make the first element minus infinity? We can either keep this 3 as 3 or make it minus infinity. We have only two choices, right? But what if we don't make this 4 as minus infinity? So this 3 will always transform to 4, this 2 will also have to transform till 4, this 1 will also have to transform to 4. So we will always have to transform to some element that is before that and that is not changed if we are transforming. So basically what we can do is we can write this state as dp of I comma j, where this means that the answer for ith till n minus 1th index, where the value just before I is nothing but aj. And also let's just make this 1 based and consider a is 0 as minus infinity. So we will solve the question in 1 based indexing and consider a0 as minus infinity. So this will store the answer this, right? Let's define this state as dpij will store the answer from I till n array where the last element before I is aj. So let's now try to make the transitions from here. So dpij will have now cases. Okay. So what will be the cases? The first case is ai is greater than aj. Let's just take less than aj. So if ai is less than aj, then we will always have to perform the operation, right? So the answer of dpij will be nothing but ci, because we are performing the operation, dp of I plus 1 comma the value will be still j, because this ai will be transformed to aj only when ai is less than aj after performing the operation. So this will be the new state, right? The next case, test case, is ai is equal to aj. So again here we don't need to perform the operation, but the state will be I plus 1 comma j only. And the next case is ai is greater than aj. So here we will have two cases that we need to take minimum of. Case 1 is we are performing the operation and doing I plus 1 comma j, and the case 2 is we are not performing the operation but the state will change to I plus 1 comma I. Why I? Because we initially had this problem I till n and we said that ai was greater than aj, right? So the answer for this case will be nothing but this I plus 1 till n and the last element was ai. So this case, or either we could have performed the operation and make this aj, then that case would be this. So these four cases we need to take care of, and we can just simply put a0 as minus infinity, and so the answer for our question will be dp of 1 comma 0, basically 1 based indexing, and we are considering the last element to be minus infinity. So this is answer, and we can just use these transitions to find using the sub problems. So for each state there are a maximum of 2 transitions and there are total number of n square states. So overall time complexity of this dp would be 2n square. So that will be the solution for this problem. I'll show you guys the code now. So this is the dp I comma j. So the cases that I talked about, if v of I is not equal to v of j. So basically not equal to v of j is these two cases. Since these two cases have this transition as common, ci plus dp I plus 1 comma j. So ci plus dp I comma 1 I plus 1 comma j, and then I will this transition is common to the case where it is greater than equal to. So when Vi is greater than equal to Vj, answer will be minimum of answer comma dp I plus 1 comma I plus 1 comma I. Yep. Basically I plus 1 comma I and I plus 1 comma j is same. I could have written here I plus 1 comma I also, because a of I is equal to aj, so it does not matter. And this line is for memoization. So memoization, and I'm taking the input vector v and c, and I'm doing v0 as minus 1e9 and taking the input as 1 based. So dp of 1 comma 0 is will be the answer, and the base case for this question would be dp of n plus 1 comma anything would be simply 0, because I don't have any further elements left, so I don't need to perform any operations. This if I is equal to n plus 1 return 0. So that was the code for problem G. So that was it for this contest discussion, and I'll end it now. Thank you.